guys, so welcome back. We are going to be talking today about chemical reactivity and all the trends that we encounter on the periodic table. And you should have gotten in your link like 3 tables, like little mini tables. At some point you'll want to look at those and either write on those through Kami or print it out and have that. That's your trend sheet. That's going to be your help sheet that you will need when you take your test, okay? And when you do the worksheets on periodic trends. So you'll want that thing that has the small, and it'll say atomic radii, it'll say electronegativity, but I sent that to you as a PDF. So please make sure you have that and you write those trends in on those different tables, okay? So in chemical reactivity, we're going to talk later when we do chemical reactions and we talk about net ionic equations about the reactivity, okay? So there's an activity series. Basically, we see that the most active metals are those in 1A and 2A, meaning that they're the ones that bond with most things and they're going to be very active on the periodic table. They're so active that in column 1, you're going to see a demo later in the week where we take a chunk of sodium, we throw it in a cup of water, it catches on fire and blows up. Now what's fascinating about that is, you know, most elements you use water to put a fire out. We've talked about this before, but those alkali metals, when they're in their element form or elemental form, they are very reactive. Even a small drop of water vapor can sometimes cause some of them to blow up. I'm going to share a video with you called the alkali metals video, and this is from a Mythbusters type thing, or no, Brainiac. That's what it was from. It's from Brainiac, and they did this. They simulated what would happen if you use rubidium and cesium and francium. We can't even get those elements. Actually, francium and cesium are locked in a lab under argon gas surrounding it, so it doesn't react with anything because they're highly explosive. Okay. So the more active the metal, the more easily it is to easily it loses electrons to form ions. Okay, so your column period 7, your francium, because it's furthest from the nucleus. We've talked about this, how the further you get from the nucleus, that pull, okay, to the center is less and less and less, right? Thinking about, like, if I go to the moon, okay, gravity, right? That gravitational pull is less and less as I get further out from the center of the earth. And so that same thing applies. So in francium, it's a whole lot easier to strip that outer electron. We just got done talking about valence electrons. So when you're forming ions, those valence electrons are actually what's getting stripped from the atom, those outermost electrons. So the ones that are going to have the further distance from the nucleus are going to be easier to strip. And so when that happens, they become more reactive with other things, okay, other elements in the periodic table. And francium is just an example of that, okay? So look at here's many periodic properties, and they vary in a regular fashion moving down a group. One example is the reactivity of the alkali metals in water. So you have lithium, sodium, potassium, rubidium, and cesium. See the difference in how they react. Huge difference, okay? Now, go to your table and look for atomic size, right? Atomic size is usually reported as atomic radius, okay? It's estimated as 1/2 the distance between the centers of 2 bonded atoms, okay? So they're going to take the center of one and measure it to the center of the other, and then they're going to half that, and that's the radius of a particular atom, okay? Now, here's the trend, okay? So as you go from the top of a column to the bottom of a column, we are increasing in size. And as we go from left to right in a period, we are decreasing in size, okay? So that's going to be our trend, okay? So atomic size increases down a group because valence electrons are in orbitals that extend further from the nucleus. The atomic size decreases from left to right, okay, because the electrons are held closer to the nucleus by the increasingly greater charge of the nucleus. So on your chart that says atomic size or atomic radius, I want you to draw an arrow on the left side that goes down, points down and says increases. Then I want you to go all the way to column 18, and I want you to draw an arrow to the left that says increasing. So I want you to do the same thing. So it's increasing this way and increasing this way. I want you to draw those lines on that smaller table that says atomic radius or atomic size. Now, atomic radius, the radius of an atom. In general, the atomic radius increases as you move down a group and decreases as you move across a period. Okay? Now, which has the largest atomic radius? Magnesium or calcium? Okay, so if we are decreasing this way, right? So magnesium and calcium happen to be in the same column, right? So we just drew a trend that says it increases from top to bottom, meaning calcium is going to be larger than magnesium. Then we have oxygen and fluorine, which are side by side, okay? But I just told you that it decreases across a period. So if it decreases this way, fluorine is on the right side of oxygen. So oxygen would be larger, okay? And then you have sulfur and fluorine, okay? Sulfur and fluorine. And they're going to kind of be diagonal, right? So we know that it increases this way, and we know that it increases this way. And sulfur's here, and fluorine's here. So sulfur is going to be larger, okay? All right, now moving on to ionization energy. Ionization energy, or they sometimes refer to as IE, is a measure of the energy required to remove a valence electron from a gaseous atom, okay? So in general, atoms with low ionization energies do not bind their electrons very tightly and are therefore very reactive. So the further you are from the periodic table, the further, the less strength you're going to have to want those electrons. And the closer you get to the noble gases, the more likely you don't want those electrons stripped, okay? So here's a chart showing you the different ionization energies, but we just want to get to the trend, okay? So ionization energy increases up a group because the valence electrons become increasingly closer to the nucleus. Ionization energy increases from left to right in a period because the valence electrons are increasingly held more tightly by the nucleus, which is increasing the number of protons. Okay, so here you go. So on your chart, you want to write it increases this way and increases this way. Okay, so it goes up and then over. All right? It's the amount of energy to strip an electron from its atom. Okay? So here, which has the greater ionization energy? Remember, it goes up and over, okay? So now, magnesium is higher than calcium in the column. So now this time, Mg is going to be greater, okay? Oxygen and fluorine, remember, increases this way and this way. So now, fluorine is going to be my greatest. And then this one, fluorine is also going to be my greatest, right? Okay, so they flipped from atomic radius. Okay, now, what do these valence electrons tell us about the stability of core or inner electrons? Okay? Since the electrons are far from the nucleus, it takes less energy to remove one. Okay? Ionization energy increases as you move across a period because the nucleus gets stronger, so it takes more energy to remove an electron. Okay? Now, the last one we're going to cover in this chapter is electronegativity. It is the ability of an atom to attract more electrons. So they want electrons because in all idea, when you look at valence electrons, everyone is trying to move over to the noble gases. The noble gases have a full outer shell, okay? That means they don't need any more electrons. That's why they don't actually form compounds, is because they don't need to lose or gain electrons because they're already stable. So all elements are trying to get over to the noble gases. As you get closer to the noble gases, you want more electrons. The metals want to get rid of electrons. Non-metals want to grab more electrons so that they become closer to the noble gas and they become stable. So in general, electronegativity decreases as you move down a group and increases as you move across a period. Okay? Or you could flip this. So we're going to do it this way. We're going to say it increases this way and increases this way. okay? Just like ionization energy. So it's going to increase this way and increase this way, okay? So, electronegativity decreases as you move down a group because larger energy levels are added that are farther from the nucleus. So the atom cannot attract electrons as well. It also increases as you move across a period because the nucleus is stronger and can attract more electrons. Because of having more electrons, you can attract more there, okay? And here is your summary of trends, okay? Just giving you an overall summary, but that's kind of a little busy. So therefore, I wanted to give you those individual tables that you can write on so that you can actually see the trends occurring. Now, we are done pretty much with this chapter at this point. This is a very short chapter. We're going to move into bonding after this, okay? So have a good day.